Hi friends, welcome to this annual refresher program in teaching. The course is on agriculture and it is on advances in agricultural engineering. So in this lecture we are going to focus on soil erosion conservation measures. So if you see that the soil erosion control measures, so broadly classified into two, so that is reducing the runoff amount and reducing the runoff velocity. So these two are the broad classifications. So under reducing runoff amount, so one is the preventing run-on. So run-on basically happens on the overland. So how to prevent that run-on? So that can help us, controlling the erosion. This is one. So under this there are diversion channels and interception ditches. These are the two soil conservation measures to control the erosion. Then the second one is like increasing infiltration. So that is through contour burns and terraces, waterways. So this will help us in reducing the volume of runoff which is taking place from the overland. So reducing runoff definitely will control the erosion or sediment flow. So then the second category, the reducing runoff velocity. So under this, the porous barriers. So oven or mat barriers, or it could be gabions. Okay, so then the second could be like concrete structures like drop structures, chute, check dams, so like that. So we are going to explain one by one in this lecture. So the first category is controlling the runoff volume. So that is our runoff amount. So under that, the diversion channels and interceptor ditches. So diversion channels, the basically if you see in this picture, so here there is a farmland and here the slopy land where we can expect the runoff from there. And that may carry a lot of eroded particles. If suppose this is the original slope, so if nothing is constructed and there is no diversion channels, what happens? The runoff can carry sediments and dumped into the agricultural fields. So that's the main thing. So in order to avoid that, so there is a diversion channel, so which is going to collect the runoff which is taking place, which also contains the sediments, and also divert to a safe outlet. Okay. So divert water away from the active gullies or critically eroding areas. This is an example. It could be act as grass filter. So grass can be cultivated here. So that will really dispose safely to the outlet. And the second is interceptor ditch. So in this is a small ditch. If you see this is interceptor ditch, small ditch which is constructed to intercept surface as well as subsurface waters. So both surface subsurface waters will be disposed of using the interceptor ditch. This is generally deeper than the diversion channels. So because we have to tap the subsurface water, so this is still a little deeper than the diversion channels. The slide soaps generally 6:1. So so the basically this is adjacent to the contours, and so the whatever water which is run off from the upstream will be collected through these interceptor ditches, and all will be disposed of to a safe outlet. And then so there is a design of the diversion or interceptor ditches. So the main the principle is the carrying capacity of the ditch. So how to know the carrying capacity? That's basically the first we will be the two cases, like determine the cross section of the channel and the design discharge or velocity of flow. These two we have to find out in this design. So, the average velocity of flow using generally the Manning's, and Manning's formula will be used for designing or the estimating the velocity of flow in the particular channel. And then the discharge capacity of the channel will be estimated using the continuity equation, that is the Q is equal to A into V, where V is the velocity which will be already having using the Manning's n, and then A is the area of cross section of the channel. Okay, so Q should be estimated for 10 years return period for agricultural land. Generally this is recommended, and length of diversion interceptor should not exceed 300 meters. So, the maximum velocity of flow should be decided based on the soil type. So, here first what we do, we estimate, we assume a channel cross section. Okay, so we using the assumed channel cross section and the slope, you will be estimating the V, and then so knowing the channel cross section, area cross section will be known, and plugging this, and this Q will be really estimated for 10 years period. So, this will be known, and A and B will be adjusted accordingly. So, finally the dimensions will be decided. Okay. And then the next is, so next category here is the increasing infiltration. So, we just finished the prevent run-on using diversion channels, interceptor ditches. So, now moving on to increasing infiltration using contour bunds and terraces. So, let us see, the contour bunds are basically the bunds which are following the contours. So, for example, here, so contours are equal elevated the points on a watershed. So, bunds are constructed along with the contours. So, basically, so from like this to this, I am sorry, and then so the bunds are constructed following the same contour. So, this contour bunds are recommended for the rainfall which is less than 600 mm, and then the slopes also having less than 6% slope. So, and whereas graded bunds are recommended for greater than 600 mm rainfall. So, the graded bund, what happens, because the rainfall is more, so you need to take off the overland flow, so safely dispose the overland flow from the the bund from the effective area of the cultivated area in between the two bunds or two contour bunds. Okay, so that is why you need to have a safe disposal or the channel in case of graded bund, and the contour bund, since we have the rainfall less than 600 mm and also the slope is less than 6%. So, that the amount of rainfall which is happening on the the land surface would be enough to infiltrate down. So, we may not be expecting much runoff. So, that is why we mostly concentrating on the bunds in this. So, let us see the how to design these contour bunds. So, the contour bunds are basically, there is a vertical interval. If you see this is a two bunds, bund 1, bund 2, which are constructed along with the contour. This is the contour 1 and contour 2, and this is the land between the two bunds. This is land between two bunds, and then this is a vertical interval. So, between the distance between the two bunds, vertical distance between the two bunds is vertical interval, and distance between the two bunds is the horizontal interval. So, the horizontal distance is horizontal interval. Okay, so how to construct what these contour bunds? So, the design basically includes estimating what is Vi, what is Hi, and what is H, small h, that is the effective or the storage depth, so, right. So, vertical interval is Ramsar's formula, that is 0.15 times S the slope plus 0.6 S in percentage, and horizontal interval Hi, that will be vertical interval divided by slope into 100. So, this is the straightforward equation. Now slope is equal to, so vertical by horizontal, that's generally into 100. So the same equation will be used here, and neglecting the minor effects due to side slopes. So I mean, if you go back and look at the the figure, so side slopes are, I mean, the interference of side slopes on water storage. If you neglect that, the storage volume SV behind the bund, so whatever the storage volume here you are seeing, so that will be that can be estimated using SV is equal to WS into H by 2. So this is kind of the triangle. This is kind of a triangle now. Okay, so if you do this, like half into base into height, right? So the same thing, half into. So here this is the I mean WS and H height. So that will give the storage volume. Okay, so assume that we are not considering the slopes here. So this is a perfect rectangular triangle. Okay, sorry, right angle triangle. And then let's see here the runoff volume RV. So RV, if you see, this is RV. So RV is generally estimated like R into HI divided by 100. So this, assume that this is, we are estimating it for 1 meter width of the land between two bunds. So that will be R divided by 100 into horizontal distance. So where R is the 24 hours excess rainfall to be stored in centimeters. Okay, so since HI is in meter, so R is in centimeter, so R by 100 will be in meters. So this will be 24-hour excess rainfall to be considered. So that's so RV, the storage per unit width you get, right? Unit width you get in RV. So now the next, what we are going to do, the previous equation and like third and fourth will be considered, say they are going to be equal now, right? So for, in order to estimate the cross section, so estimating RV and SV from equation 3 and 4, because these two should be equal. Okay, WS into H by 2, this is storage volume, R into HI by 100, this is runoff volume. So from this you can get H is equal to R into HI by 50 divided into WS. So from the similar triangular figure, so if you see this, this is one triangle, at the same time this is another triangle. So this is the two similar triangles, So so WS by, so let's say WS by HI, WS by HI is equal to H by VI, H by VI. So this is similar triangle principles. From here, WS will be just manipulating the equation, you get H into HI divided by VI. Okay. Now equation from 5 and 6, you can estimate the H value in terms of vertical interval and R. Okay, so one is horizontal interval, you get I mean, if you're using horizontal interval you can get H, at the same time using vertical interval also you get H. Okay. And the next is a bench terrace. So in bench terrace, so divide the slope hilly, so if the slope is more than 6%, so we are going to use bench terrace. So that means the hilly areas are cut down into different benches of different sizes. The almost the equal sizes we follow. So if you see here, the main components of bench terrace will be, there is a riser, and then there is an outlet channel, and there is a platform, and there is a shoulder bund here, right? So this is basically the original land. The original land is being cut into here this portion will be cut and this portion will be filled basically. Okay. So, and there is a shoulder bund to avoid runoff, and whatever runoff which is collected here, since it is a flat, so the water will be collected here, then this will be disposed of. Okay. So, let us see how we can so basically design this. If you see the terrace spacing, so this is one of the important thing, terrace spacing. So, basically the maximum depth of cut D, small d is the maximum cut off depth. So, for example, this is the small d. Okay. This will be decided based on the type of crop, so because the root zone depth will be decided because this portion, the flat portion, will be used to rise crops, right. So, the depth basically will be decided based on the type of crop and the productive soil. So, soil like the depth of soil which is productive to produce the or to cultivate the crop. So, based on these two parameters will be deciding the maximum depth of cut, and let d will be the effective depth, like that is d is equal to 2d. So, basically we are cutting from top to bottom of the foot, that will be 2d. So, that is 2d, and the horizontal distance will be 100 into d by s. So, this is the vertical interval, and then the horizontal interval will be so that will be 100 into d divided by s. S is the slope. So, this is simple equation, S the slope equation. From there you get the horizontal distance. So, for example, W is the width of the bench. So, this is the width of the bench, and then suppose the slope is 1:1, the horizontal distance will be W plus D, this will be the effective horizontal distance. So, that will be equal to 100 d by s. So, this is 100 d by s. So, vertical distance, similarly vertical distance is equal to d. So, d can be estimated from this equation. So, W s by 100 minus s. So, if the riser slope is half is to 1. So, and this formula, so half is to 1. So, this formula will be turned into this way, W plus d by 2 is equal to 100 into d by s, where vertical interval is equal to W s by 200 minus s. So, based on the side slopes for riser, you can estimate the vertical interval knowing the horizontal the distance, the horizontal distance. Okay. Alright, so that is vertical and horizontal. So, the next is gradient. So, terrace gradient will be basically estimated using the rational formula. So, the area of the terrace that has to be drained out of the by the channel. So, this will be area, the total area will be length of the bench, width of the bench divided by 10,000, because this is a meter square, you have to convert that into hectares. So, that is area into hectares you get, and then you are going to use rational method to find out Q, because using the step number 1, knowing the area, and Q is equal to CIA by 360. So, here CIA, so this already I think we explained in the previous lectures. Okay. So, substituting the values you get Q value. So, that is the QP, the peak value. So, the peak runoff we can expect from the basically the bench. Okay. This is the runoff, and then non-erosive velocity V, using the standard tables, from standard tables you will be knowing what is the safe disposal velocity for that particular soil, right, soil type as well as the crop, right, and the cross sectional area AC from table 2 steps 2 and 3 will be used to estimate the cross sectional area A. So, that is the continuity equation. Using the continuity equations, because knowing the Q and then knowing the V. So, Q is equal to A into V, right. So, then area of cross section will be known. from step number 2 and 3. So, appropriate channel and suitable dimensions will be assumed. So, here assume the particular cross section, right. From knowing the area of cross section, you can assume suitable dimensions. Now, decide the grade of the channel using the Manning's equation. So, this is known, and this is from your tables, from the standard tables. Now, S will be fitted to round off safe velocity in the channel. Okay, that's a non-erosive velocity. So, this way the grade will be estimated for the bench terrace. And the next is vegetative waterways. So, vegetative water, these channels are used basically what happens if you see this picture. So, there is no vegetative waterways. If there is no vegetative water, we may expect the entirely the soil, removal of soil from the overland, from the the overland, right, surfaces. So, similarly, so if you have this grassed waterways, this portion of grassed waterways, and having particular shape, and we may expect the whole thing looks like this. Okay. So, these are the channels used for carrying excess runoff from the cropland safely without scouring the channel beds and sides towards the outlets. Okay. So, waterways also provide outlet channels. So, not only helping the safe disposal of the overland flow, but also it also like provide outlet channels for constructed terrace systems, contour cropping, and diversion channels. So, so we can still use the vegetative waterways in the previously whatever we talked about the soil measuring structures. Okay. And consider the establishing the graded waterways when working with the water sheds greater than 20 hectares. So, this basically recommended for the watershed of area 20 hectares, more than 20 hectares. The shapes could be a triangular or trapezoidal or parabolic. We see this is kind of a parabolic, but we also have the triangular and trapezoidal kind of waterway shapes. And the next is the design of vegetative waterways. So, if you see that basically we will be using the safe disposal velocity as well as the continuity equation for designing this. So, this already we talked just few slides ago. So, step 1, assume the flow depth and calculate the channel cross sectional area, meter perimeter, hydraulic radius and width. So, basically you have to assume a particular shape for constructing the waterways, and so knowing the particular shape, we know the design dimensions or the design parameters. And then the mean velocity V using Manning's equation. So, that is generally we for grassed waterways N is equal to 0.04. So, so R you will get it from then is assumed cross section, and then the S value we have to assume again. So, for a particular grassed ways in the soil type, you will be knowing what is the velocity, the mean velocity or same mean velocity, and the discharge will be estimated using Q is equal to A into V. Check Q within the permissible range and V is safe. These two things we need to check. First, see whether Q is within the permissible range. So, we already explained how to estimate Q. So, Q is equal to using the rational method. So, let us see whether this Q, estimated Q is in the permissible range or not, and also V is safe or not using this equation. So, repeat step number 1 with different flow depth if Q and V are unsafe. So, this is kind of a trial and error method. So, you have to go back and adjust the dimensions and then redo the calculations. So, till you satisfy the V and Q. So, and once everything is done, I mean design dimensions are done. So, you are going to add freeboard for 15 centimeter the channel depth. So, this is the safe in order to avoid any unusual rise in water depth. Okay, so then the second category here, see, reducing the runoff velocity, that is through porous barriers. Porous barriers are oven and mat barriers are gabions. So, let us see the different types of porous barriers here, temporary gully structures. So, one is here oven wire check dams. So, if you see in this, so the boulders or the rocks are constructed like the semicircle, and this is also a semicircle case. So, the water which is taking place will be passed through this, depositing some and again depositing some soil here, and you get the safe water going back. All right. So, the dam is built in half moon shape with the open end upstream. It is suitable for moderate slopes, which is less than 10%, and small drainage areas. And this is mostly widely used when in the stony areas, like where there are the rocky areas, because the rocks should be available to construct this. And the other one, the second one is brush dams. So, this is mostly is suitable for the areas where the woody areas, like the forest areas. The small gullies are 1.2 to 2 meter deep with small drainage area, and the cheap and easy to build, but at least suitable for all type of check dams. So, this is basically going to reduce the water flow by providing these partial dams like brush dams. So, you can reduce the flow velocity of flow. So, the sediment will be deposited here. So, this is brush dams, and then the next is the loose rock dam. So, the loose rock dam have longer life than brush dams. So, if you see here, the rocks are really sacked and laid across the cross section, and this is suitable for gullies with small and medium sized drainage area. And here if you see that there is other possibilities of planks and slab dams. So, if you see here, is the vertical planks will be series of vertical planks will be planted or the posted along with that, and make a partial dam here, okay, a barrier kind of thing. So, this is going to arrest the big velocity or the velocity of flow, and really just a little bit more, a little bit small. So, that way you can control the sediments here. Okay. Okay, so and then the final category here is the concrete structures. So, that will be drop structures, chute and check dams. So, these are mostly, I mean, if you see, these are most effective kind of soil soil erosion control measures. Let us see. So, here the first one is drop spillway structures. The drop spillway structures, it basically contains a particular weir kind of a rectangular weir kind of masonry structure. So, it is going to have the apron, wings, side walls. Okay. So, water which is really falling is going to drop down. So, the drop could be like limited to 3 meter. Then after that it overflows here, and then there are some wing walls like that. So, that is going to divert the flow to the downstream basically. Okay. The drop structures are used along the gully bed to act as control points. Okay. So, that gully bed is not eroded below the crest level of the structure. So, this if you see, this is the gully. So, in order to avoid the sediment flow in the downstream, so the drop spillway really helps. The flow in drop spillway passes through a weir opening. So, this is a weir opening and falls or drops in approximately level apron. Okay, this is the apron or stilling basin and then passes into the downstream channels. Okay, so that way it works. So, main components are here. There is a weir, apron, like this is the weir and this is the apron and this is the side walls and this is the big wall. This is the big wall here. Okay. Okay, so the next structure is a chute spillway. The chute spillway, so when you have it's a larger drop. So, for example, 3 to 6 meter drop you expect, that means highly slopy areas. So, these chute spillways are really effective. It generally consists of an inlet, a vertical curve section and the steep slope channel and outlet. So, here there is an inlet and vertical curve section and steep channel, okay, and then there is a outlet here. Okay. So, this is more effective, the slope of the land is higher, okay, and for drop it will be 3 to 6 meters you to use. The capacity chute spillways are cheaper than the drop spillways as they require less construction material. So, and also this is not complicated. So, it's construction is easy. So, inlet and then there is a spillway and then after that the fall and then there is a outlet. So, it's not so complicated design compared to the drop spillways. Drop inlet spillways. So, what happens if you have the depth is more than 9 meters. So, you are going to use the drop inlet spillways. So, in this there will be like a pipe type or box type the inlet. So, the water will be this is inlet, water will be go down and then pass through this and from there this is the outlet. So, the excess water will generally pass through this, okay, and this is practiced in G4 type gullies and difficult to construct because it has a difficulty in the sense relative to the chute spillway and drop inlet spillways. So, because there is a there is an inlet pipeline, so there is a careful design is required. And this is also known as a shaft spillway because there is going down and there is a shaft inside. This is a shaft spillway. Okay, so those are the structures and so there are how to estimate the soil loss from a watershed. So, soil loss generally estimated using the universal soil loss equation. So, here the universal soil loss equation generally represented with this equation, that is A is equal to R K L S C P. So, these are the factors. So, the first this is the soil loss per unit area in unit time, but unit time here is mostly what we are talking about is the annual. So, okay, so annual erosion, soil erosion from an area is estimated using universal soil loss equation, and R is the rainfall erosivity factor and K is the soil erodibility factor and then L is the slope length factor, S is the slope steepness factor and C is the cover management factor and P is support or practice factor or management factor. Then so see, this is an empirical equation. Okay, so because the units, if you see, units are not matching, but the finally this is after getting the data, this is fitted into this equation considering different factors. The prediction of annual soil loss from a watershed, and this is non-computation of gully erosion. Okay, this may not be used for gully erosion, and non-computation of sediment deposition. This doesn't deal with sediment deposition principle or anything. So, it does not give any idea on whether the sediment is deposited somewhere or transported to another place. So, there is no spatial distribution of sediment load in a watershed, but it will give the total at the end of the watershed or outlet of the watershed. So, then Williams 1975 is modified this equation to make it more useful with the storm based equation. So, this is USLE, this is called modified universal soil equation. So, that is y is equal to 11.8 into q. So, this whatever the rainfall erosivity factor is been replaced with 11.8 into q into qp into 0.56, and the rest all parameters are same. So, this y is the sediment yield from the individual storm in metric tons. Okay, this individual storm you get this yield, and q is the storm runoff volume and qp is the peak runoff rate. So, qp will be estimated using rational method, and then the applicable to induce erosion due to individual storms increases sediment yield prediction accuracy compared to your universal soil loss equation. The daily, monthly and annual sediment yields of watershed can be modeled in this. So, because this is pointing the storm based sediment yield, so this can be used to estimate sediment yield from a watershed either daily base or monthly base or annual basis. So, this is modified universal soil loss equation. So, in this lecture what we learned was like what are the soil conservation measures or soil erosion control measures. So, we talked about the broad classification and we went into different the measures, and finally the sediment estimation, sediment yield estimation at the watershed outlet. So, using universal soil loss equation and also the modified universal soil loss equation. So, this will be more this will be used basically to understand or estimate the soil erosion from a storm, that is modified soil loss equation. Okay, so thank you so much.